Welcome back. Today we're gonna look at section 4.4, which is coordinate systems. And as before, a lot of the stuff in chapter 4 we've actually talked about before. We're just going to be expanding on it, thinking about it in terms of vector spaces, and also some extra ideas in terms of just matrices in RM as well. So, coordinate systems. First, remember a couple of terms that we've got. We've got a basis, when we leave this term, basis, span we've talked about. So remember that a basis is, our notation is usually this script B, and it's a set of vectors, B1, B2, all the way to Bn. And the basis for a vector space is, remember, a linearly independent spanning set. So these vectors are all linearly independent, and they span whatever vector space we're looking for. So that's where we've got to start. So a couple of things that we can ask about these things. So suppose a script B, V1, V2, all the way to Vn, is a basis for a vector space V. And you really can think about this vector space V right now as just Rn, or R4, R2, or just anything that we're used to. So we've got a basis, a fundamental set that we can use to create anything else. Suppose that we've got some vector x, which is also in this vector space V. What does it mean in the vector space V? What does it mean to be a basis? It means that any vector can be written as a linear combination of those elements. So then x is some combination of these vectors, c1, b1 plus c2, b2 plus cn, bn. So this is what it means to be a basis. Any vector that's in the vector space can be written as a linear combination of the basis vectors b1 through bn. Not only that, these coefficients, the scaling factors, c1 through cn, are unique. Right? There's no other way to make x using the vectors b1 through bn except for with one specific set of scaling factors. That's because these vectors are linearly independent. If vectors are linearly independent, then any different scaling of those vectors will lead you to a different a resulting vector. So remember back from chapter 2, what we say then is that the coordinates of the vector x relative to the basis b are c1 through cn. So c1 down to cn. So x relative to b are these scaling factors c1 through cn. In practice, it doesn't lead to anything particularly tricky. Right, so let's just look at a simple example. So here is a basis for R2. This is a basis for R2 because it's linearly independent and it's two vectors. So one points on the x-axis, one points 45 degrees out. They are linearly independent, they point in different directions, and they span everything because there's only two vectors and we're only making R2. So they span everything. This is a basis. Let's find the coordinates of the vector x relative to the basis b for x equal to the vector 3 minus 1. So let's remember, what are we actually asking for? We're saying what we actually need is we need to say that x has got to be c1 b1 plus c2 b2, where this is b1 and this is b2. And so in order to find c1 and c2, that's what we need. These will be our coordinates of x relative to b. So c1, c2 will be x and b. In order to solve this, I can think about this as a matrix equation. b1, b2 multiplied by c1, c2 here. This matrix multiplication becomes c1, b1 plus c2, b2. And so what we actually end up having to do is to solve the matrix equation 0, 2, 1, 1, and then the vector x, which is 3 minus 1. We need to solve this. We're really thinking about this now as c1, c2, which we row reduce. And if we row reduce this matrix, what we get is this following matrix. And remember, so this reads C1 is negative 2 and C2 is 3. So C1 is negative 2, C2 is 3, which means that XB is minus 2, 3. Now let's take a second and check. If we actually plug these things back in to C1 and C2, what would happen? So C1 is negative 2. When I multiply through here, I get negative 2 plus 3b2 is 3, so I get 3 in the first entry. And then negative 2 times 2 is negative 4, plus 3 over here is negative 1. And in fact, this equation is satisfied. Let's look at another one. Suppose that our basis, we're going to have a basis for R3. Suppose this is our basis B for R3, and our goal is to find x sub B, the coordinates for the vector x, relative to this basis, if x is the vector minus 1, 2, 0. That's our goal. Again, remember, how can we be sure that B is in fact a basis? Well, we could be sure by row reducing the matrix given by the column vectors created out of the basis vectors V. If I would row reduce this, we end up with the identity. And that's what we want if we're going to have a basis for R3. If we're going to have a basis for R3, we need a linearly independent spanning set. Linearly independent spanning set. Linearly independent means a column in each, a pivot in each column. To span, we need to think about that as saying that the linear transformation is onto, which means that it's got to have a pivot in each row, and that's only going to happen if it row reduces to the identity. So this is in fact a basis for R3. If I would like to find the coordinates of this vector relative to this basis, what we're doing is simply solving that matrix equation. Matrix created out of the vectors B, the final column is the vector x, and then row reduce and see what we get. And what we get is the following. And so what that tells me is that the coordinates of x relative to the basis b are 5/7 minus 1/7 minus 6/7. All right, so one more piece here. We could ask it in the other direction. I could say that suppose that we know the coordinates relative to the basis, what was the original vector? All right, so we also have to be able to go the other direction with these as well. Suppose that I give you a basis for R2. So here is a basis for R2. So this is a basis because they point in different directions. One is not a multiple of the other. So I have a basis for R2, and suppose that I also give you the coordinates of a vector relative to this basis. Suppose that the coordinates of this vector are 3 minus 2. So let's find the vector x. Well, the whole point here is that if these are the coordinates, the vector x is in fact the coordinates of coordinates relative to the basis scaled by these entries. So 3 times 2, 1. Right, so this is my basis. So I have this is the coordinate of the first vector, and this is the component of the second vector. So plus minus 2 times minus 1, 2, which I could rewrite, notice, as 2, 1 minus 1, 2, a matrix made out of the basis multiplied by the coordinate vector xp, 3 minus 2. And what I get is 6 plus 2 is 8, and 3 minus 4 is minus 1. And we're done. All right, so to summarize, in slightly different notation, what we've actually already seen. Right, so notice that we saw that really all that we're looking at is if B is a basis, B1 through Bn, because we use this so much in what we just discussed, I'm going to turn this into a matrix, and I'm going to call it the matrix P sub B. And that's our matrix B1 through Bn. And then in terms of this matrix P sub B, any vector x is just P sub B times the coordinates of x relative to the basis B. Because this is our B1 through Bn, and the coordinates relative to the basis are the C1 through Cn. So this together makes C1 B1 plus C2 B2 plus all the way out to C to B, Cn Bn. So that's C1 B1 plus all the way to Cn Bn. And that's exactly what our vector x is. But also notice that this matrix is invertible. And it's invertible because it's a basis for our vector space, which means it's linearly independent and it spans everything, which means that it has a pivot in every row and a pivot in every column, which means that it's an invertible matrix, which means that I can actually multiply by PB inverse on both sides. And what we now have is a way of solving for the coordinates for x relative to the basis B. So in terms of this notation, all we need to do is make the matrix PB and then either multiply a vector by that matrix or else multiply a vector by the inverse of that matrix. So just let's apply that to an example. All right, so let's consider the basis for R3 given by 0, 1, 1, minus 2, minus 2, 3, 0, 2, 1. A. For x, 1, 2, negative 3. let's find the coordinates of x relative to b. Coordinates of this vector relative to the basis x. That is b. That is, we're looking for the C1 through Cn. In this case, C1, C2, and C3. That's what we're looking for here. So remember that x as a vector is PB coordinates of x relative to b. We're asked to find this, so this equation doesn't quite work. We actually got to use the other form by multiplying by PB inverse on both sides. But if we do that, then we have the coordinates of x relative to the basis b. So what we really need is, we need the inverse of that matrix multiplied by the vector x. And that's something that we can do by hand, or we can put into our calculator. This is much easier because we're dealing with an inverse, actually just to put into our calculator. So I'm just going to put this matrix right into my calculator. We're going to put the matrix PB into the calculator. That's 3 by 3. Now remember that once I've got it into my calculator, I can do anything that I need to do just from the home screen on the calculator. So I'm not going to put this onto the screen, but all that I'm going to do is I put this in, I stored it as matrix A. I'm going to take A inverse multiplied by the vector 1, 2, 3. So I also need to put the vector 1, 2, 3 in. So I'm going to make that a different matrix. We're going to make that the matrix B. And that's going to be 3 by 1. And just 1, 2, minus 3. So now from the home screen, I'm just typing A inverse times B. And we don't have to do any other work, except for maybe convert it to fractions, because we will have some fractions. And the answer is minus 4/3, minus 1/2, minus 1/6. So you should make sure that you know how to do that on your own calculators. I just stored this as matrix A. I stored this as matrix B. And then I typed A inverse, don't forget about your inverse, times B. And this is what we get after we convert it to fractions. We also have to be able to go the other direction. That one's actually a bit simpler. Now we have to be able to go the other way as well. So suppose that we were told that we know what the coordinates of x relative to the basis B are. Suppose these coordinates are minus 1, 2, 3. Then find the vector x. Not in brackets, just the vector x. Then find x. Well, remember that x is PB xB. So that is just 0, minus 1, 1. Minus 2, minus 2, 3, 0, 2, 1, multiplied by xb, which is minus 1, 2, 3. And so now we just need to take this matrix times this vector. So I've already got A stored, this matrix stored as A in my calculator. So I do have to change the matrix B. So minus 1, 2, 3, and then after I do that, I just need to take A times B. And what we get is minus 4, 3, 8. Okay. All right, and that's all we need from 4.4. Next, we'll move into 4.5. All right, so in 4.5, we are worried about dimension. Again, another one of these words that we've seen before in chapter 2 and the end of chapter 1. And this one is mostly review, just thinking about it again, sometimes from a slightly different angle. When we think about it from the vector space angle in general. But so remember that our definition of the word dimension the dimension of a vector space is the number of elements in any spanning set. So we have I shouldn't say spanning set, I should say in any basis. A basis is a linearly independent spanning set. So the number of any elements in any basis. Remember, we're not going to prove this again, but if I have two different bases for the same vector space, then they actually have to have the same number of elements. So this number of elements in any particular basis is what we call the dimension of the vector space. Right, so it's how many different vectors we need to start with in order to use those as linear combinations and create absolutely everything. Now we've seen this word applied to a few things already. Right, so remember that for a matrix A, then we have a couple of vector spaces that we've associated to this matrix. We have the column space of A, which is the span of the columns, and we have the null space of A, which is all of the vectors which get sent to 0. Remember that the dimension of the column space of A, is the number of pivots in A, and the dimension of the null space of A is the number of non-pivots, the number of non-pivot columns, which is the same thing as the number of free variables in the matrix equation AX equals 0. Remember, it doesn't make sense to talk about free variables unless we actually have an equation. If I just have a matrix A, there's no equation. But if I'm looking at AX equals 0, then we have an equation, so we can talk about free variables. Okay, so let's let V be the span of these vectors. So what is the dimension of V? So we're going to take this and make the matrix. We're going to row reduce. And this is what we get. So this is our row reduced matrix. We have one pivot, so the dimension of V is 1, which shouldn't be a big surprise based on what we see, because this is a multiple. Both of these vectors here are multiples of the first vector, so this is the only one that's needed. Everything else can be made out of that first. In fact, what we actually have is just a line through the origin. V is just a line through the origin. Suppose that this is the matrix A. Let's find the dimension of the null space of A, and also a basis for the null space of A. Okay, so when we're talking about the null space of A, we're looking at the matrix equation AX equals 0. So we're looking at A0, which we row reduce. So I'm just going to make the matrix A with an extra column of zeros, so that's 3 by 5. And then I'm going to row reduce. And what I get is this matrix. Then with a column of zeros as well, which I can't fit. 0, 0, 0. So that's the matrix that we get. In terms of free variables, we see one free variable. So the dimension of the null space of A is just 1. Remember how we actually go about finding a basis for the null space of A. This is x1, x2, x3, x4. So that reads x1 is equal to negative 2/3 x4. x2 is 4/9 x4. x3 is 32/9 x4. So my vector x is actually x4 times minus 2/3, 4/9, 32/9. And this vector here is a basis for the null space of A. It's one-dimensional. One-dimensional means that it's a line, means that it's all multiples of a single vector. So it's all multiples of this particular vector. So in this example, let's look at our polynomial vector space P4. Remember what this is. This is all polynomials of the form C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the fourth. Where these things can be anything. So remember that in this case we actually allow C4 to be any number. It might even be 0, which means that we may only have a cubic, but it's still considered part of P4. All right, so here's a couple of things about it, based on what we've done this section and the last section as well. All right, so first of all, what is the dimension of P4 as a vector space? Well, the dimension is the number of elements in any spanning set. Right, so what set might actually span this? Remember that a basis for P4 is actually just the polynomial 1, the polynomial x, x squared, x cubed, and x to the fourth. This set forms a basis because anything in here is a linear combination of these vectors. Because if I took these vectors or these polynomials, we're thinking about them as vectors because this is a vector space, and scale them and add them up, then I can make any fourth degree polynomial. So 1, 2, 3, 4, 5, what we actually get is this dimension is 5. The dimension is 5. Because it takes 5 vectors. To create anything. And so we'll end this section by talking through two true-false questions from the text. And to get a better idea of what's going on, these require us to do a bit more thinking and less writing down, and just understanding what's happening. So 19a, the number of pivot columns of a matrix equals the dimension of its column space. Well, that's true, right? The dimension of a column space is the number of pivot columns. So when I talk about the column space, I'm talking about the span of the columns, but I don't need all of the columns. I just need any columns which show up as pivot columns, because the other ones are extra and can be made out of the pivot columns. So 19a is true. B, a plane in R3 is a two-dimensional subspace of R3. That's false. It sometimes is true, but remember, to be a subspace, we actually also need to contain the 0 vector, and not all planes in R3 contain the 0 vector. So planes that go through the origin in R3, they in fact are two-dimensional subspaces. They're two-dimensional because it only takes two vectors to create the entire plane. In fact, any two vectors that point in different directions will work. So a plane that goes through the origin is a subspace of R3 and its dimension is 2. But any other plane is in fact not a subspace. C. The dimension of the vector space P4 is 4. Well, that's false. We actually just looked at that a minute ago on the whiteboard. The dimension of P4 is actually 5 because we also need to include the constant polynomial 1. So our basis is 1, x squared, x cubed, and x to the 4th. So we actually have 5 elements in our basis, so the dimension is 5. Part D. If dimension of V is n, and S is a linearly independent set in V, then S is a basis for V. Well, that's not true. That's false. We would need S to be a linearly independent set that has n elements in it. Right? So just a single vector is linearly independent by itself, but it's certainly not a basis. We need a linearly independent spanning set to make a basis for V. E. If a set V1 through Vp spans a finite dimensional vector space, and if T is a set of more than P vectors in V, then T is linearly dependent. That's true. Right, so if I've got P vectors that span the entire vector space, and then I add more, well then I certainly have a linearly dependent set, because what I add more I could have created by using V1 through Vp. So E is false. And we'll also talk through number 20. A. R2 is a two-dimensional subspace of R3. This is false. R2 is just the vectors with 2 elements in them. R3 is vectors with 3 entries in them. They're not the same at all. I can't say that R2 is contained inside of R3 because R3 is vectors with 3 entries. R2 is vectors with 2 entries. So it doesn't even make sense to say that R2 is a subspace of R3 at all. B. The number of variables in the equation AX equals 0 equals the dimension of null A. No, the number of free variables in that equation is the dimension of null A. C. A vector space is infinite dimensional if it is spanned by an infinite set. Well, that's actually false, right? I could have a set, suppose we had a matrix that had 8 column vectors. That doesn't mean that, in fact, the dimension is 8 because some of those column vectors could be extra. I could have R3 is a spanning set for R3 could be every single vector in R3, but I don't need them all. So every single vector in R3 does in fact span R3, so that's an infinite dimensional set that spans R3, but since I don't need them all, it's not an infinite dimensional vector space. D. If dimension of V is n, and S spans V, then S is a basis for V. Well, no, that's not true, for the same reason as before. S could have too much stuff in it. It could have too many vectors. S might span V, but include more than I actually need. In order to be a basis, it's a linearly independent spanning set. That is, it's a spanning set that has as few as possible elements. E, the only three-dimensional subspace of R3 is R3 itself. Yes, that's true. If I have 3 linearly independent vectors in R3, then the span of those vectors is in fact R3. There's nothing else left. There's no space for anything else, so E is true. All right, and so that's section 4.5, and see you next time for 4.6. All right, and so we are going to move into section 4.6, which is called rank, which we've talked about before. But we're also going to talk about something new, which is called the row space. So remember from before that the rank of a matrix is the dimension of the column space of the matrix, which is the number of pivots in the reduced row echelon form of the matrix. All right, so that's the first thing. And so based on that, we can say that the rank of A plus the dimension of the null space. This is pivots, columns with a pivot. This is columns without a pivot, so this is the number of columns of the matrix. Okay, now as far as a new thing, we're also going to talk about what we're going to call the row space of a matrix. And so the row space is just the span of the rows. The span of the row vectors. Column space, we're used to thinking about span of the column vectors, and that's fine, and we think about column vectors as these columns, and the span of those is the column space. The row space, though, is just the span of the rows going across. So there's just a few tricks or tricky things about what's happening. So if I have, say, this matrix, right, so if this is my matrix A, row A is the span of the column of the row vectors, but we're going to write these vectors as rows going across. Is the span of 2, -1, 1, 0. So these are now what we're going to call row vectors, vectors going straight across. We can think about it really is just it's just entries, right? We've got, this is a vector in R4, there's 4 entries, but we're writing them going across because they come right off of our matrix going across. 3, 0, 1, 2, and 4, 1, 1, 2. All right, so that's fine. Now, we have a couple of different things that we could ask. We could say, what is the dimension of the row space? And what is a basis for the row space? So the dimension and basis for row A. Okay. Now, so how are we going to do this? We can do this a couple of different ways. So let's start with dimension. Notice that if I have a matrix, let's just go with one that's a little smaller for now. Here's a matrix, and suppose that I apply a row operation. Right, that is a row operation that's in the middle of row reducing this matrix. Right, what might we do? We could scale. Right, we could scale by a constant. We could multiply and add. Suppose that we took this one. Suppose that we took row 1, negative row 1 plus row 2, row 3, and put it back into row 3. Right, in order to turn this into a 0. Then we have 2, -1, 0, 0, 3, 1, 0, 2, and 1. Right, so this is a row operation that we might have done at the beginning of row reducing the matrix. Right, but notice what's happened here. Right, so our new row 3 is a linear combination of row 1 and row 2, of the old row 1 and row 2, old row 1 and row 3. We took row 1 and row 3, we scaled row 1, we added it to row 3, we put it back into row 3. So this new row 3 is a linear combination of the old row 1 and row 3, which means that the row vectors here span the same thing as the original row vectors. So the row space of the new matrix is the same thing as the row space of the original matrix A. So we haven't changed the span of the row space by applying a row reduction operation. And that's true for all of our row reduction operations. If I just scale a row, that certainly doesn't change the row space. And if I multiply, if I scale and add, well, that creates something which is a linear combination of the original, so that doesn't change. And if I switch 2 rows, well, that also doesn't change the row space. It doesn't change the span of the vectors. So all of our row reduction algorithms will not change the row space. And so what that means is the row space of A is actually equal to the row space of the reduced row echelon form of A. And when I have a reduced row echelon form, it's actually very easy to see what vectors we need in a basis. So let's look at that with an example. Suppose that this is my matrix A. Suppose that this is my matrix A, and suppose that I row reduce this matrix okay. This is what I get. Okay, so now remember we're looking at a row space, so we're thinking about rows rather than columns. And I say, and I say, well, if I thought about these as rows, which of these things would be necessary? Where would the pivots be? But now when I'm talking about pivots, I'm not looking at pivots going this way, right? Because that's what we were looking at when we were talking about a column space. Now I'm talking about if I were to look at it coming this direction. If I were coming this direction, I'd have a pivot still here, here, and here, but the whole vector would be included. So every single thing, every single row would correspond to a row that is necessary. So what does this tell me? This tells me that in the end, since the row space of our matrix A is the same thing as the row space of these things, and these three rows are linearly independent because each row has its own pivot in it, that I can say that these three vectors form a basis for row A. Notice that I didn't pull off the rows from the original matrix. I didn't pull those rows off. Now, in this case, we could have, but we're going to look at some examples where it's different. The point is that when you row reduce a matrix, sometimes you actually switch the position of rows. So if I would have switched row 1 and row 3, and then I end up getting a pivot somewhere but not in the other row, then I don't know where it came from originally. So we have to pull our basis elements off of the final resulting reduced row echelon form when we're talking about the row space, rather than from the original matrix. But I can say for sure that the dimension of the row space of A is 3, because I have 3 row vectors that end up being linearly independent. Let's look at another one where things are a little bit different. Okay, so let's use this matrix and ask, what is a basis for row A? And as well, what is the dimension? But if I have a basis for any vector space, then I know what its dimension is because I just count the number of elements that are in the basis. All right, so our process is to apply our reduced row echelon algorithm. So if we create this matrix and reduce row echelon form it, what we get is the following. So this is what we get as the reduced row echelon form. So at this point, now we're looking at rows going across. I see a pivot here, and I see a pivot here, so my dimension is actually 2. Right, So the dimension of row A is 2. And a basis for row A are the column or the row vectors 1, 0, 14, 9 and 0, 1, 1, 9 as row vectors. I can't say that the original 2 rows here are the correct rows, again, because there may have been some row switching going on when we row reduce. And so maybe the one that's not necessary is the middle one that's got switched to the bottom or something like that. So you can't go from the reduced row echelon form, you can't decide which of the original ones you could use. You would actually have to go back through the whole process and keep track of which rows got switched around in order to do that. But it's much easier just to look at the end result and say that these are the vectors that it would take to create the row space. All right, and that's what we need from this section, 14.6. We'll move along to 14.7. Okay, so we're going to look at the last section in chapter 4, section 4.7, change of coordinates. And here's our basic idea. Suppose that we've got some vector space V, just think about this as R2 or R4 or Rn if you'd like, and we have 2 different bases. Bases is the plural of basis. It actually looks like bases, but you pronounce it bases. So 2 bases, B and C. So B and script C, both of which are a basis for the vector space V. So this means that for any vector x in V, I have 2 different coordinates for the vector x. I've got x sub B, and I've got x sub C. And so a natural question might be, well, is there an easy way to go back and forth between the 2? So if I know the coordinates for the vector x in terms of B, what can I do to get them in terms of C, and the other way around, if I know some relationship about these different things. So let's look a little bit more specifically. All right, so suppose that we have 2 different bases for R2. So the first basis we'll call B, and this will be 1, 1. Actually, let's not even be so precise just yet. Suppose that we've got 2 different bases, B1, B2, and suppose that we've got a basis for a second basis, C1, C2, both of which are going to be bases for R2. Suppose that I know a little bit more. Suppose that I know the relationship between these vectors already. Suppose that I can say I know that B in terms of C1 and C2 is 2C1 minus C2. And I know that B2 is C1 plus 3C2. If x has coordinates relative to the basis B of 3 minus 1, let's find the coordinates of x relative to the basis C. I will be able to do this. So what we're given here is the relationship, a relationship between these 2 bases. Right? So notice that if I have a basis B, vectors B1 and B2 that span all of R2, I can always write them as a linear combination of this. B1 has got to be able to be written as a linear combination of C1 and C2 because this is a basis, which means everything can be written as a linear combination of C1 and C2. So B1 can, and so I've got it, and B2 can as well, and so I've got that. So we're given this information, how to write B1 and B2 as a linear combination of the basis vectors C1 and C2. We're also given the coordinates of some vector x relative to the basis B, and asked to find the coordinates of x relative to this new basis, the other basis C. All right, so we can actually do this, and this is going to help us get to a more general technique. Okay, So what do we have, right? So if the coordinates of x relative to b are 3, -1, that means that x is equal to 3 times b1 plus -1 times b2. This means this. Now that's what that means. If I have coordinates relative to a basis of some constants, that means that those are the scaling factors for b1 and b2, which make the vector x. So that's what we're told. But now we know what b1 and b2 are in terms of c, so I can redo this in terms of the vector c. So this is 3 times 2c1 minus c2 plus -1 times b2, which is c1 plus 3c2. And so what we're going to do here is just expand everything out, combine like terms. Notice that we have 6c1 minus c1, which is 5c1. We have -3c2, and we have -3c2, which is -6c2. So 5c1 minus 6c2. Now, let's also notice if I created the matrix, I'm going to look at b1 relative to c. Well, we were told what that is. We were told that b1 was 2c1 minus c2. So the coordinates of b1 relative to the basis c is 2 minus 1. And we're told that b2 relative to c, well, here's b2. It's c1 plus 3c2, so that's 1, 3. So I'm going to make this matrix out of these two things. 2 minus 1, 1, 3. All right, so this is just b1 relative to c, b2 relative to c. And if I multiply by x relative to b, what we started with, that was 3 and minus 1. Notice what we get. So this is x relative to b. We get 6 and minus 1, which is 5. We get minus 3 and minus 3, which is minus 6, which is exactly what we got up here. So up here we were told that x is 5c1 minus 6c2, which tells us that x relative to c is 5 minus 6, which is exactly what we get down here. And so let's put this together in general terms. This is how it's always going to work. If we know the relationship between the two bases, so in this case we knew how to get b, if we knew the coordinates of each b vector relative to c, and we could use that to convert any b vector to its coordinates in c. All right, so in general, so we'll have a vector space V. We'll have a basis for the vector space B, which will be B1 through Bn. We'll have a different basis for the vector space V, which will be C1 through Cn. We're going to have a relationship between B and C. So if we know the coordinates of each B vector relative to C, so we know each B vector relative to C. These are all known. Then we're going to create a matrix out of these things. And so this matrix is going to be B1 relative to C through Bn relative to C. The coordinate vectors of each of the basis vectors B relative to the new basis C. And this is a matrix, and we're going to call this, the matrix is going to have a funny sort of notation. Right? We're actually going to write it like this. It looks a little bit backwards, but there's a couple of reasons why, and we'll talk about those in a second. But we're thinking about, this is a matrix that we're going to use to convert B coordinates to C coordinates. So we're taking B and we're converting them to C. And so, and again, how is this done? This is done by starting with B, the original basis vector is B, and looking at their coordinates relative to C, and we get this. So it looks like we're going backwards here, and we'll talk about why that notation works like that. But for now, that's what we've got. Right, and so what we can say then is then for any x in V, the coordinates of x, if you know the coordinates of x relative to B, then I can convert them to the coordinates of x relative to C by multiplying by this matrix P, which converts B to C. We're going to do a couple of examples, a bunch of examples of this, but this is in fact exactly what we just did a minute ago with the basis vectors B and C, the very specific ones that we were given. But this already shows us why we write this notation like this, because this B here has to match this B here. That's why we put it on the right, down over here, because we actually multiply by a matrix on the left. So then we're taking a B vector and converting it to a C. We're inputting a B vector and it gives us a C vector, or C vector that's out over here. Because we multiply by a matrix on the left, that's why this notation looks like it does. All right, so let's do some examples. So we'll have a vector space V. We're going to have two bases. B will be B1, B2, and B3. C will be C1, C2, C3. And suppose that we're told that B1 is C1 plus C2 minus C3. B2 is 2C2 plus C3. And B3 is C1 minus 2C3. If the coordinates of x relative to B are 1, 1, 1, find the coordinates of x relative to C. So this is almost exactly the same thing that we did this before, but now we're just going to go right to making the matrix and using it. Right, so this tells me that the coordinates of B1 relative to C are 1, 1, minus 1. The coordinates of B2 relative to C are 0 for C1, 2, 1. And the coordinates of B3 relative to C are 1, 0, minus 2. Okay, so we're going to use that. We put those into a matrix. So my matrix is P, converting B to C, and that matrix is the matrix that we get just by lining those up. So then P from B to C of a matrix X, if I know its B coordinates, are the X in terms of the C coordinates, because I've converted B to C. Right, so now we were given XB. It was 1, 1, 1. And we were asked to find XC, and so we just multiply and see what we get. We get 1, 0, 1, which is 2. We get 1, 2, 0, which is 3. Minus 1, 1, and minus 2 is minus 2. And so that's the answer. Okay, so here's one that requires a few more steps. Suppose that now all that I'm going to give you, so we're going to now look inside of R3. We're going to say that B is some very specific vectors. So that's B, and we're going to have the basis C, which will also be some very specific vectors. So that's C. So now let's find the matrix P, which will allow us to convert B to C. So that's what we need to do, which means that we need to know what are the coordinates of B1 relative to C, what are the coordinates of B2 relative to C, what are the coordinates of B3 relative to C. So really what we're doing is, remember, how do I say, so if I want the coordinates of B1 relative to C, then what I'm really doing is saying 1, 2, 1, minus 2, 1, 3, 0, 2, 4. That is the C basis. And then I'm row reducing, I'm setting that equal to the B vector. And then figuring out what the solution to that system of equations is. So if we row reduce that matrix, what we get is so this is what we get, which tells me that the coordinates of B1 relative to C are 0.2, negative 0.4, 0. So let's save that over here. If I wanted the coordinates of B2 relative to C, we're doing exactly the same thing, but now we're putting B2 over here. So I'm just going to edit the matrix and change it so that I have B2 at the end, 2, 2, 3, and see what we get. What we actually get when we row reduce, the only thing that changes is that last column, and that last column now is 0, minus 1, 1.5, which means that the coordinates of B2 relative to C are 0, minus 1, 1.5. And finally, if I want the coordinates of B3 relative to C, then what we do is we change this very last column to B3, 0, 0, 4, and see what changes. And what we get is that this becomes minus 1.6, minus 0.8, 2. So B3 relative to C is minus 1.6 minus 0.8, 2. Which tells me that I now know what the matrix P is. P, which converts B to C, is these columns. 0.2, minus 0.4, 0, 0, minus 1, 1.5, minus 1.6, minus 0.8, 2. Now, we did that, we took a lot of time, and we worked that all out piece by piece in order to get these three things separately. Let me just point out that we could have done this all in one step. So note, I could have actually just taken this matrix here, row reduces down to the identity. right? That's always going to happen because these things form a basis. And if you take a basis and you row reduce, you get down to the identity. So I could have actually just started with 1, 2, 1, minus 2, 1, 3, 0, 2, 4. And I could have put a second matrix over here on the right, right? And that second matrix would have, all that I would have needed was the entries for B1, B2, and B3. And so those vectors were 1, 0, minus 1, 2, 2, 3, 0, 0, 4. Right? So this was B1, B2, B3. Right? This was C1, C2, C3. So I start with this. If I row reduce this, these things are going to turn into the identity, and these things are going to turn into exactly the column vectors that we need them to at the end, because this column isn't affected by anything that happens over here. The only thing that's going to it worries about is what's happening over here. So essentially what I'm doing is I'm row reducing all three of these at exactly the same time. All right? So if I row reduce this matrix, and you can try this, put it into your calculator and see what happens. When you row reduce this matrix, what you end up getting is the identity on the left, and on the right, you get these vectors, or this vector, this matrix in the end. 0.2, minus 0.4, 0, 0, minus 1, 1.5, minus 1.6, minus 0.8, 2. And so this is P, which converts B to C. And this gives us another reason why we actually write this backwards, converting to the left. Because when we apply the process, we put the C vectors, then we put the B vectors in that order. And then we row reduce and see what we get over here on the right-hand side. All right, so we'll do a few more like that, but before we do that, let's use this to actually answer a question. So for this particular situation, suppose that I said if the coordinates of x relative to the basis b were the vectors 3, 0, minus 1, let's find the coordinates of x relative to the basis c. But the coordinates of x relative to c are P, which converts B to C, times the coordinates of x relative to B. Which means that what we've got is this matrix here, 0.2, minus 0.4, 0, 0, minus 1, 1.5, minus 1.6, minus 0.8, 2, multiplied by 3, 0, minus 1. And you can work that out if you want. Whatever you get when you simplify that is the answer. This will be the coordinates of x relative to the basis c. All right, so let's do another one from the top. Okay, suppose that our, let's just look at R2. Suppose that we had a basis for R2 given by 1 minus 2 and 0, 3. And we had another basis for R2 given by 1, 2 and minus 1, minus 4. If the coordinates of x, let's do two things. If the coordinates of x relative to b are 1, 4, let's first find the coordinates of x relative to c. In order to do that, so we're given the b coordinates, we need to find the c coordinates, which means that we need to find the matrix P, which converts B to C. But remember, this matrix is created by lining up the vectors in basis C, 1, 2, minus 1, minus 4. Then lining up the vectors in basis B, 1, minus 2, 0, 3. We row reduce. We find the identity on the left, and we see what we get on the right. As it turns out, for this particular matrix, when we row reduce, we get 3, 2, minus 3 halves, minus 3 halves. And so this matrix over here on the right is our matrix P, which converts B to C. So let's save that. So P from P to C is 3, 2, minus 3 halves, minus 3 halves. Which means if I have a vector with coordinates in basis B, I can convert B to C by multiplying by this matrix. So we have the vector 1, 4. We want to convert it over to C. So that tells me that XC is P, which converts B to C, times the vector 1, 4, which is 3 halves, or 3, 2, minus 3 halves, minus 3 halves, times 1, 4, which is 3, minus 6, which is negative 3, and then 2 minus 6 as well, which is minus 4. And so that's the answer. And finally, let's do one last thing with this. We're going to keep the same situation, that same basis B, same basis C. So we've calculated the matrix which converts from B to C. Suppose that for part B of this question, I said if the coordinates of the vector x relative to C now are 2, minus 4. Right, so remember, in the first situation, I gave you the coordinates of x relative to B, and we could use this matrix to convert to C. But now I'm giving you the coordinates relative to C and asking to convert to the coordinates relative to basis B. So that's what we'd like to do. But so the idea here is that the coordinates of x relative to C are exactly this matrix, P, which converts B to C, multiplied by XB. So if I want to find XB, that's what I want. I've got this equation and I want to know this. I'm going to multiply by the inverse of this matrix to bring it over to the left. So I get the inverse of this matrix, with P, which converts B into C. So inverse multiplied by coordinates of x relative to C, and I get the coordinates of x relative to B. So that's what we wanted to find. That's our goal. We have coordinates of x, C. We have this matrix P. So we can just put that into our calculator even to see what we get. And so the answer will just be this matrix times 2 minus 4. So the coordinates of x relative to B are going to be 3, 2, minus 3 halves, inverse times 2 minus 4. And that's something which we'll have to, it's easiest to do just by putting these things into our calculator. And then just multiplying. And this is what we get. And so that's the answer. And that's what we need to talk about for these sections. That's 4.4 through 4.7. Next time we'll be looking at chapter 5, some eigenvalues and eigenvectors, some new stuff, new words, funny sounding words. I will see you then.